What if the most compelling proof of alien intelligence isn't buried beneath the dust of Mars or hidden in the glow of a faraway galaxy, but rather encoded in the atmospheric chemistry of a world just 124 light-years from Earth? Not fiction, not fantasy, actual verified data, captured by the James Webb Space Telescope and decoded by a cutting-edge quantum artificial intelligence, has unearthed something so unexpected, even the most restrained scientists are stunned. Within the atmosphere of the exoplanet K218b, researchers found molecules that, frankly, shouldn't be there. Not unless life put them there. This marks the first real fracture in the long silence of the universe. A potential signal that could redefine not just how we perceive life beyond Earth, but how we understand our place in the cosmos. The breakthrough didn't come from a grand broadcast or blinking lights on a radar. It came from a forensic deep dive into starlight. JWST's NIRIS and NIR-spec instruments captured light filtering through K218b's atmosphere during a planetary transit, offering a chemical snapshot of what's present. At first, astronomers were scanning for common gases, carbon dioxide, methane, but what emerged went well beyond that. Faint, but distinct, the spectral signature of dimethyl sulfide, DMS, and dimethyl disulfide, DMDS, showed up. On Earth, these compounds are almost entirely linked to life, especially marine microorganisms like phytoplankton. And this wasn't some marginal, could-be coincidence. A quantum AI, specifically trained to identify complex chemical entanglements in noisy spectrographic data, isolated the DMS signal at over 3 sigma confidence. That's not a maybe. That's the kind of clarity scientists dream of. But this discovery is just the beginning. K218b isn't your garden-variety exoplanet. Discovered in 2015, it's classified as a Hycean world, a type of super-Earth wrapped in a hydrogen-rich atmosphere and likely covered by a global ocean. Think of Earth, scaled up and cloaked in thick, swirling hydrogen clouds. Back in 2019, Hubble hinted at water vapor, but the data was too grainy to confirm much. Then came Webb, its far more precise instruments cracking open a door that had only been nudged ajar before. While several AI systems helped interpret the deluge of incoming data, it was a custom-built quantum AI from a Geneva lab that made the difference. Unlike classical models, this AI didn't just search for known molecular fingerprints. It explored the abstract relationships between spectral line behaviors, nonlinear, multidimensional harmonics that most human scientists couldn't even begin to map. What it uncovered wasn't just a set of molecules. It found a pattern that looked eerily biological. The research team from Cambridge put forth a bold theory. The DMS and DMDS could be the byproducts of alien microbes living in a vast subsurface ocean, excreting sulfur-based compounds into the atmosphere. Here on Earth, phytoplankton and certain bacteria do exactly that. So what if, on K218b, the same thing is happening? Starlight slicing through the planet's clouds then carries a whisper of those life signs across the galaxy, right to our instruments. Adding weight to the theory is the presence of methane and CO2 in the same atmosphere. When taken together, these chemicals start to form a coherent biological fingerprint. But the scientific community isn't unified just yet. There's a counterpoint, and it came swiftly. Shortly after the Cambridge team went public with their findings, researchers at Oxford conducted their own independent reanalysis of the JWST data. Their results? They couldn't replicate the DMS or DMDS detections at all. According to their models, the chemical signals might be nothing more than artifacts, quirks caused by overlaps in JWST's detectors or biases in how the data was modeled. Worse still, the DMS signals lack supporting compounds typically found alongside biologically produced sulfur, like nitrogen-based byproducts. Without them, the signal's credibility plummets. It was a gut punch. What had looked like the most promising biosignature ever observed might just be a mirage. Or might it still be real? Here's where the stakes escalate. This debate goes beyond whether a couple of molecules exist on some remote world. It dives into how we define life itself, and more importantly, how we detect it. For centuries, we've asked if we're alone. Now, with quantum-enhanced AI and telescopes a million miles from Earth, we may finally be in a position to answer. But that answer comes at a cost of hope, of potential disappointment, of pushing science to its limits. Cambridge sees a pattern: DMS, methane, and now a third candidate, ammonia, all appearing together. To them, it's not just a cluster of molecules. It's a signal, one far too precise to be dismissed. The Geneva AI didn't merely flag the compounds. It decoded correlations, resonances, and time-sliced fingerprints in the data, connections no human model would likely catch. Still, Oxford isn't wrong to question it. Their caution is rooted in discipline, not denial. Extraordinary claims demand extraordinary proof. They argue that quantum AI may suffer from epistemological overreach, an elegant way of saying that just because the AI sees patterns doesn't mean those patterns are real. It could be hallucinating, a well-structured illusion formed in high-dimensional mathematics, but physically meaningless. That's the paradox. The same complexity that gives quantum AI its edge also makes it a potential source of error. It doesn't just analyze data differently, it thinks differently. It builds frequency webs across time, detects co-absorbed compounds, and maps resonance harmonics. These patterns might represent biological activity, or they might just be the echoes of the AI's own logic. Trusting it means stepping into the unknown. And now, the next piece of this puzzle is already on the way. The JWST's MIRI instrument is being retargeted toward K218b, aiming to scan in the mid-infrared, where molecules like ammonia and DMS shine more clearly. With longer observation windows, deeper integration, and tighter noise control, MIRI could either confirm or dismantle everything we think we've found so far. Because if MIRI sees the same molecules, if ammonia shows up in expected abundance ratios, or if it appears independently on a completely different instrument, then the AI's findings gain enormous weight. Multiple instruments, multiple methods, same conclusion. At that point, even the skeptics at Oxford will have to take notice. Right now, we're in a state of scientific limbo, a moment where skepticism and cosmic wonder stand side by side. The countdown to MIRI's scan has already begun. While we wait, speculation continues, because discovery doesn't sleep. And just as this tension was peaking, a quiet leak slipped out from within the European Space Agency. A whisper, a hint. The MIRI spectrometer might have already detected ammonia in the atmosphere of K218b. For many, ammonia isn't particularly exciting. It's in cleaners, fertilizer, your fridge. But in a planetary context, everything changes. On a hydrogen-rich world like K218b, ammonia isn't supposed to stick around. It should be broken down by sunlight or neutralized by other chemical processes unless something is actively replenishing it. On Earth, that something is life. Microorganisms, particularly in the oceans, excrete ammonia as a byproduct of nitrogen metabolism. Its presence in K218b's atmosphere could point to the same process happening out there. And if true, it becomes the third major biosignature detected in the same environment. Methane, DMS, and now ammonia, all linked to biology here on Earth. And just as MIRI's raw data was being crunched, Geneva's quantum AI was already running early passes through it. What it found was jaw-dropping. Resonance patterns in the ammonia signature match specific atmospheric pressures that, in theory, would allow liquid water to exist beneath the clouds. Add in the other signals sulfur and nitrogen cycling, stable atmospheric chemistry, and suddenly we're not talking about mere habitability. We're talking about the active machinery of life. Not aliens sending signals. Something smaller. Something quieter. Alien plankton. Microscopic organisms. Alive. Thriving in a hydrogen ocean under swirling clouds, on a super-Earth orbiting a red dwarf 124 light-years away. That's not a fantasy. That's the shape of the data. And what makes it even more powerful is convergence. These aren't isolated flukes or anomalies from one glitchy detector. They're appearing across different JWST instruments at different wavelengths, detecting different chemical species, all leaning in the same direction. And that direction, straight toward life. For perhaps the first time in human history, we're moving beyond speculation. This isn't just about vague signs or ambiguous hints. It's about concrete chemical fingerprints, layered one atop the other, forming a portrait that looks more and more like biology. K218b is no longer just another interesting dot in the star chart. It's emerging as a real candidate for something extraordinary. the first known world beyond our own that may harbor life. Let's pause and really consider what's unfolding. Dimethyl sulfide, methane, carbon dioxide, and now ammonia. Each of these molecules can be found elsewhere in the universe through non-biological means, but not like this, not together, not in these ratios, and not on a planet that appears to have the right kind of environment to support life. When we see this cocktail of compounds on Earth, it means only one thing. Something is alive. But science is careful. It doesn't leap, it climbs. Step by validated step. Which is why replication is everything. Right now, follow-up analyses are being prepared, reanalyses of old datasets, refined simulations of atmospheric chemistry under hydrogen-rich conditions, even lab experiments here on Earth to recreate K218b-like environments. The goal? To determine whether these chemicals could arise without biology. Could volcanoes, photochemical reactions, or exotic mineral interactions explain what we're seeing? So far, the answer leans toward no. Ammonia, in particular, is a game-changer. On K218b, bathed in ultraviolet light and nestled in a volatile atmospheric soup, ammonia should be chemically unstable. Without an active, continuous source, it should vanish quickly. That it's being detected at all, and possibly in measurable quantities, implies something is actively producing it. Combine that with methane, which also degrades quickly in hydrogen atmospheres, and the case begins to solidify. Something may be maintaining this chemical balance. And there's more. The Geneva AI isn't just throwing out molecule names. It's mapping relationships, patterns of covariation between compounds, atmospheric pressures, temperatures, and light absorption features. It's identifying rhythm. Life isn't static. It fluctuates, it breathes, it cycles. What the AI appears to have found isn't just the presence of life-friendly chemicals, but the dynamic dance between them, cycles that hint at biological processes. Let's not overlook the uniqueness of this moment. This isn't some blockbuster alien encounter with blinking lights and flying saucers. This is quieter, subtler, and possibly far more profound. We're not hearing words. We're not seeing cities. We're reading the invisible breath of microscopic organisms in alien air. Imagine what this says about life in the universe. If biology can arise on a mini-Neptune orbiting a red dwarf star, wrapped in a hydrogen atmosphere, then the rules for life just exploded. It doesn't require Earth-like conditions. It doesn't need sunlight as we know it or an atmosphere like ours. It might only need chemistry, warmth, water, time. And if that's true for K218b, how many other worlds might fit this broader, more inclusive definition of habitability? Because here's the kicker, K218b is just one of tens of thousands of exoplanets we've cataloged. If it's showing potential biosignatures already this early with just a few years of JWST data, then the floodgates might just be beginning to open. What happens when we start scanning other Hycean worlds? What happens when quantum AI gets even better at filtering out noise, correlating across wider datasets, and identifying even more subtle markers? We may be standing at the dawn of a new era in astrobiology. One where life isn't rare, but inevitable. Where biology doesn't need a perfect planet, just the right chemistry. Where microbial ecosystems might be bubbling away, invisible and ancient, on worlds we once overlooked. But for all the excitement, caution still rules the day. Scientists from multiple institutions are preparing more rigorous modeling work to explain, or debunk, these findings. Some are attempting to simulate how JWST's detectors behave under different observational conditions. Others are experimenting with new cloud models to test whether known physics could replicate what looks like a biosignature. And skeptics continue to raise valid concerns. Is the Geneva AI truly seeing what's out there? Or is it simply finding complexity in complexity? Because with quantum AI, we're entering a frontier where our own tools may outpace our understanding. When an algorithm points to something biologically plausible, but does so using logic structures no human can fully audit, we find ourselves in new philosophical territory. Do we trust the signal? Or do we wait until independent methods verify it? That's where MIRI's deeper scans will prove critical. A completely different slice of the spectrum, less prone to interference, more sensitive to compounds like ammonia and DMS. If it detects these molecules again, especially in the same quantities, the argument shifts dramatically. At that point, we'll have redundant confirmation from separate detectors across different wavelengths using independent analytical methods. That's not just suggestive. That's strong. And if another telescope, say the upcoming ELT, Extremely Large Telescope, or the Ariel mission, confirms the findings, then we're looking at one of the most important discoveries in scientific history. A second genesis. Not of intelligence. Not yet. But of life. Simple, thriving, alien. If even a fraction of this evidence holds up under scrutiny, we're on the verge of something monumental. The first confirmed detection of alien life. Not in a petri dish, not in a lab sample, but through the atmospheres of distant worlds. And unlike the kind of life we imagined in science fiction, intelligent beings communicating with radio waves or visiting in ships, this is something different. More primal. More universal. Life as chemistry. Life as persistence. Life as the inevitable result of a planet doing what planets do under the right conditions. And that idea that life may be a natural consequence of physics, not an outlier, shakes the foundations of everything we thought we knew. It suggests that biology isn't a fluke, but a feature. It may mean that for every rocky or ocean-covered world orbiting a stable star, there's a chance, a real one, that something is swimming, replicating, metabolizing, or even evolving beneath its clouds. But K218b is just one data point. It's where the curtain first started to lift, but it won't be the last. And researchers know this. That's why the search is broadening. The same quantum AI systems, now validated by their first major trial run on K218b, are being pointed at other candidates, planets like GJ1214b, LHS1140b, and a few in the TRAPPIST-1 system. These are planets that also fall within the so-called Hycean or super-Earth categories, worlds with either deep oceans or thick atmospheres that might shelter life. What makes this new generation of AI so transformative isn't just its speed or sensitivity. It's the way it reframes the question. Classic analysis asked, what molecules are here? Quantum AI asks, what invisible patterns suggest biology? It doesn't need to be told what life looks like. It learns what relationships in spectral data might indicate a living system. Coabsorption curves, nonlinear entanglements between trace gases, pressure fluctuation dependencies. It builds a model not of molecules, but of metabolism. And that means it can see things we've never seen before. It's already helped identify unexplained harmonics in the TRAPPIST-1e data. Nothing conclusive yet, but enough to flag it for deeper study. And as each new telescope comes online, Ariel, Roman, and the ground-based monsters like the 30-meter telescope and ESO's ELT, our ability to scan and confirm will grow exponentially. Soon, we won't just have one or two flagged biosignature candidates. We could have dozens. Yet with each candidate comes a deeper philosophical shift. Because this isn't just a hunt for microbes. It's a redefinition of what life means. On Earth, biology is rooted in carbon, water, and nitrogen cycles. But what we're beginning to see is that similar dynamics may emerge in entirely different planetary environments. Hydrogen-rich skies, high-pressure oceans, trace sulfur and nitrogen chemistry. It's alien, but familiar enough. That resemblance, that's what's terrifying and beautiful. It says the universe isn't just habitable. It's alive. But not everyone is ready for that idea. Some scientists warn that we may be jumping the gun. That we're interpreting noise as signal, that we're letting the technology outpace the theory. And to an extent, they're right, because this is new ground. We've never had instruments this sensitive, algorithms this powerful, or data this rich. The temptation to rush to conclusions is enormous. Every discovery brings attention, headlines, funding. And yet, the best minds in the field know this only means something if it survives the crucible of replication and peer review, which is why the data is being poured over again and again across institutions, across continents, in labs and models and telescopic reobservations. It's why even the quantum AI's own processes are being audited by physicists and computer scientists, trying to ensure that the patterns it sees are real and not the hallucinations of mathematical overreach. And still, through all that scrutiny, the signal persists. What's truly revolutionary about this moment isn't just the potential discovery of life. It's the method. This isn't a chance meteorite with fossil imprints. This isn't a blurry photograph or a radio blip. This is repeatable, scalable. It's a system, an architecture for detecting life from a distance, using photons and algorithms alone. Think of what that means. For centuries, we've wondered what alien life might look like. Now we might finally have the tools to find it, and not just in our backyard but across the galaxy. Quietly, precisely, by detecting its breath in the atmosphere, its chemical exhalations, the subtle fingerprints left in light. This is the turning point from the age of wonder to the age of detection. And as more planets enter the search zone, the big question becomes, how common is this? Is K2-18b rare? Or is it simply the first of many? Because if it's the latter, then the implications are staggering. It would mean that life doesn't just happen, it wants to happen. That given the raw ingredients, nature will mix them until something wriggles, divides, and evolves. And if that's true, then the universe isn't empty. It's teeming. Future missions and the expanding search for life. As we've seen, the James Webb Space Telescope, JWST, has already provided the first significant clues in this cosmic hunt for life. But this is just the beginning. Future missions, both space-based and ground-based, will continue to push the boundaries of what we know. JWST's follow-up observations with its MIRI mid-infrared instrument will help refine our understanding of K2-18b's atmosphere. But this is only a piece of a much larger puzzle. In the coming years, missions like the Nancy Grace Roman Space Telescope and the Ariel mission will continue the search for life in exoplanet atmospheres, each with their own specialized instruments and tools designed to dig deeper into these atmospheres. For example, the Ariel mission will focus on studying exoplanet atmospheres in detail, potentially detecting even more complex molecules that could point to biological processes. Ground-based observatories, like the Extremely Large Telescope, ELT, and 30-meter telescope, TMT, will also play a crucial role. These massive instruments will provide us with higher resolution images and better atmospheric data, allowing scientists to directly study exoplanet atmospheres in ways that are currently beyond our capabilities. Beyond that, the possibility of sending probes or landers to nearby exoplanets to analyze their surfaces, perhaps sampling soil, atmosphere, or even looking for signs of life in oceans or ice, becomes more real with each new breakthrough. But as technology improves, we also need to think about the ethical, philosophical, and practical implications of what we might find. The ethical and philosophical implications. If we confirm that microbial life exists on other planets, whether it's in the oceans of K2-18b, the clouds of Venus, or some other distant world, the implications will be nothing short of revolutionary. For millennia, humanity has pondered whether we are alone in the universe, and the discovery of alien life would fundamentally reshape our understanding of our place in the cosmos. Ethics of exploration. If we find evidence of life, microbial or otherwise, on another world, it raises questions about how we should proceed. Do we protect these potential ecosystems as we have on Earth, or do we continue exploring and extracting resources as we have on other planets? Should we actively search for signs of life, or should we hold back, respecting the unknown ecosystems we encounter? The role of AI. The increasing reliance on artificial intelligence in this search introduces a whole new dimension. Quantum AI has already proven its usefulness in detecting complex patterns in data that would have been impossible to uncover with traditional methods. But as we use these AI systems more, we must ask whether we're ready to trust machines to identify signals of life. Could AI, in its complexity, misinterpret data or find patterns that aren't there? The risk of over-reliance on AI is something scientists will need to navigate carefully as they continue to make these monumental discoveries. Existential reflection. And, perhaps most deeply, the discovery of alien life forces us to confront our own existential questions. It challenges our beliefs about life, creation, and even religion. The very idea that life could emerge independently elsewhere challenges the idea that humanity's biological makeup is a cosmic anomaly. It could usher in a new era where humanity redefines its place in the universe, not as the sole proprietors of life, but as one species among many that have arisen in a universe teeming with possibilities. The changing landscape of science. As we move forward, the method of discovery is equally as important as the findings themselves. What we're witnessing is a shift from traditional astronomy to a more data-driven, AI-assisted science. Quantum AI is not just helping us see data in a new light. It's teaching us to think about data differently. Where humans once looked for individual signals, AI is finding patterns and correlations that span across multiple datasets and instruments. It's this pattern recognition, along with multi-instrument validation, that could help confirm whether these unusual chemical signatures are indeed biological. This process reflects the broader trend in science, the integration of cutting-edge technologies to enhance human capabilities. We're moving into an era where the tools we build to explore the universe are as essential as the curiosity that drives us to ask big questions. Science is evolving. It's no longer just about looking through telescopes and studying distant stars. It's about building machines that can sift through massive amounts of data, pulling out the signals that matter, and using those insights to rewrite the rulebook. Concluding the topic. So, where does this leave us? The discovery of potential biosignatures on K218b is one of the most significant steps in the search for life beyond Earth. But it's also a reminder of the larger, ongoing scientific journey we're all a part of. We're standing at the edge of something incredible, something that could redefine our understanding of life, the universe, and everything in it. But we're not there yet. The evidence is compelling, but it's still early. What we're really seeing is the dawn of a new era of discovery. The data is there and it's real, but we still have to verify it, replicate it, and, most importantly, understand it. We're learning to listen to the universe in ways we've never done before, and that's a thrilling, humbling experience. This isn't about proof yet, it's about possibility. And the more we probe, the more we'll uncover. It's a journey that will continue to evolve, and in the end, it may not just change our understanding of life elsewhere, it may change how we view ourselves. The universe, once silent, is starting to speak, and we're finally starting to listen.